In section 1.2, we are going to take a look at the basic of functions and their graphs. Speaking about function, we first need to understand what function is. Let's take a look at the definition. I have that on the screen already. A function is a correspondence from a first set, we call that domain, to a second set, we call that range, such that each element in the domain corresponds to exactly one element in the range. I pay attention in here, so exactly one and in the range right here. All right. So let's take a look at some example. For functions presentation, we have different kind, not only equation, but also we can use set, graph, etc. For instance, the first example I wanted to show it to you is the function is written as a set notation. 0, 1, so they are order pair. So the 10th, 6.7, 20, 10.6, 30, 13.2. So that is the functions. Let's take a look at functions. What is the domain of these functions? Domain are the input, which is the first element in the set. So those are the domain elements. So the domain is the set contained all the elements of the input. So that's the domain. And the range for this function is all the output is the second element in the order pair. 9, 6.7, 10.6, and 13.2. That's the range for these functions. Let's take a look at another two functions. So let's take a look at this one. 1, 6, 2, 6, 3, 6, 4, 9. Right. Similar idea. If we take a look at its domain, there are a collection of all the inputs. So 1, 2, 3, 4. By the way, set, the order is not matters, so you can switch the order inside the set. Range is 6. Well, this is also 6, but we don't list the repeating element, so we just put 1 6 in here and then 9. So that is a range. So those are functions. You can see each input only corresponding to an output. Each input is corresponding to output. So this is a function, and also this is a function. Let's take a look at another example. And this time I'm just going to swap the order of these two elements. So the way it looks like 6.1, 6.2, 6.3. Well, I made a mistake. I said let's look at another function, right? It's not necessary. So take a look. This first way I know that is a relation. Let's see if it's a function or not. 6 is an input corresponding to 1. But wait a minute. 6 corresponding to 6 corresponding to 3. So in this relationship, that the input 6 have not only one element in the range, so therefore is not a function. So that's as a set. Let's take a look at a function, write it as an equation. Okay. Let's take a look at some example. So with the example in here, we only consider at this moment x is your input, y is your output. Let's take a look at the first one. Y squared plus 4 equals x. So is this a function? Let's take a look. The idea is that every x has a corresponding one y corresponding to it. Not necessary. For instance, I'm going to give you a counter example, which proving is not true. For instance, if y equals 1, x will be equal to 5, right? So 5 corresponding to 1, and also if y equal -1, also phi is -1. So this is not a function. Let's take another one. How about I swap that? I say x squared plus 4 is equal to y. So for this case, yes, it is a function because for every single input is corresponding to exactly one output. So this is a function. Indeed, later on we will learn that is a quadratic function. Sorry, I just noticed that the screen is not displaying. And let's go back to what I talk about as an equation. Example, y squared plus 4 equal x. We say it's not a function because, for instance, I give you one example when x equal to 5, but you have two outputs corresponding it. So it's not a function. X squared plus 4 equals y. This is a function, and later on in this, I think it's chapter 2, we are going to know that this is a quadratic function. Okay. So there's a functions written as the equations. How to express the functions in a general? We are going to take a look at the function notation. So you see this one a lot in a lot of math book. What it meant is not f times x. That means it's a function. This function name is f, and the input is x. So function f of x. So the way we read that is f of x. For instance, let's take a look at some examples. F of x is equal to x squared plus 4x plus 5. What does this function mean is if you have a functions f, whatever the input you put in, you use the input squared and plus 4 times the input and then plus 5. Let's take a look at some variable. And then we are going to evaluate f of 0. So in this case, what is my input? The input is 0. So that is a 0 squared plus 4 times 0 plus 5, which is equal to 5. So the output is 5. In other words, for these functions, if input 0, output will be 5. We can explain that in order here. Let's take a look. How about f of 1? F of 1, that means input square is 1 square plus 4 times input is 1 plus 5. So that is give it 10. How about the input? Let's change to -1. So the input, whole input is -1 squared plus 4 times -1 plus 5. So that's the same as 1 minus 4 plus 5. That will give us 2. So when the input is -1, the corresponding output is 2. What if the input is just a symbol b, which we call variables? Then your input is b, right? So by the definition is input squared b squared plus 4b plus 5. Take a look at these functions outputs. They have no line terms, therefore we cannot combine them. How about f of -x? What does that equal to? Input is -x squared plus 4 times -x plus 5. Therefore, square, the negative become positive, x squared minus 4x plus 5. Let's take a look at another one. How about f of x plus 2? This time, the whole input is this whole expression x plus 2. Therefore, that's equal to x plus 2 squared plus 4 times x plus 2 plus 5. Okay, you can simplify that, but at this moment we just keep that like this. Alright, so those are the functions definition and what is the notation for the functions. Let's take a look of the graph of function. So right now we are talking about the graph is located at the rectangular coordinate, which is we cover in section 1.1, right? So we are talking about the graph on this coordinate place. So the first thing, let's take a look of vertical line test. And we can call that VLT. Is that if any vertical, which is up and down line, intersect a graph in more than one point, then this graph does not define as a let's say call y as a function of x, right? So that's a vertical line test. So what's the vertical line test? Let's take a look of some example. I'm going to give you some graph, and let's determine if they represented the functions or not. At this moment, we don't need to worry about how to write that in an equation to display this graph. Okay, for instance, this is y, this is x, that's 0. This is function g, let's say g of x, that's the y. Okay, so you can see what the vertical line test means. Okay, imagine you have a vertical line can move left and right, right? So if you can ever see this line intersect the line, the graph more than one point, then it's not a graph, a function. But in this case, well, the maximum intersecting the line is 1 point. So therefore, this graph is a function. Therefore, g is a function. Let's take a look at another graph. Okay, so this graph looks like that. Let me call that f of x. Okay. Let's see if f of x is a function, not y is a function of f or not. Well, I really don't like to say that call the f of x because that might be misguiding you. Is a function of x. Let's say this is just y, this graph. Okay, ignore that notation. Now in this case, you can see if I pass this line, oops, any of this line after this point, we've intersect the graph in more than 1 point with 2 points, right? For instance, I just take a look here, or if you have a line right here, then intersect more than 1 point. Therefore, I can conclude this one, it is not a function. Let's take a look at one more. And I have a horizontal going to here. Let's take a look if this is a function or not. Now, vertical line test, 1 point, 1 point, 1 point, 1 point. So the only one have some argument is this one, right? Alright, mathematically, few circle indicated including this point, and open circle indicated not including that point. Therefore, indeed, it looks like intersecting at 2 point. Indeed, this one is still intersecting at 1 point. So this it is a function. Okay, so that's the vertical line test for that. Let me write down what I meant in here. So the closed dot is including the point. And this is opened. So it's opened dot, that means exclude the point. You see some of my graph have an arrow on it, so the arrow is indicated in this direction infinitely. Okay, so it's extend indefinitely in the direction in which the arrow points. So those are the basic idea of a graph of functions. And let's take a look at some more characters of the graph. The domain and range. How can we define the domain and range from the graph? Just keep that in your mind that domain is the collections of all the input, and then range is the collection of all the output. So with that in your mind, take a look at this graph. I'm going to use an example to explain to you. So X is all the input and Y is all the output. So I have a graph maybe going like this. Is a function, pass a vertical line test, and here is corresponding to the point. Let's make up a number -3, and this is 10, and maybe this is 1, and this is 4. So the domain is all the input which is from left to right. So we are going to write that as an interval notation for this problem. So the domain in here, the most left point is -3, the most right point is 10. -3, that's dark, close dark, so we're including -3 but exclude 10. Range is Y, so it's the interval on the vertical way. So the lowest point is 1 and the highest point is 4. Lowest point including because of the closed dot, highest point is excluded because it's an open dot. So that's range. Keep in your mind when you write the interval, the left side is always the least number and the right side is always the greater number. So what I use in here is the interval notation. But this is not the only way to indicate a set, okay, or the domain range. We can also use set builder notation. I'm going to use the same example. First, in the domain, we know that is between -3 and 10, right? So how can we write a set notation? Think about this number is X greater than or equal to -3 and less than 10. So I can use set builder notation X such that X is greater than -3 and less than 10. So that's called set builder notation. And then similarly idea, my range can be written as Y such that Y is greater than or equal to +1 and less than 4. So that is the domain. And in section 1.1, we also talk about the x-intercept, y-intercept of the graph. Right? I want to add one more thing in the x-intercept since we are looking at the graph. In this x-intercept is the graph intersected at x-axis. So take a look at this. So those points intersected at x-axis, they call x-intercept. And also we learned that on x-axis, all the y value is equals to 0. So therefore, x-intercept, sometimes we can understand that is the zeros of a function. Well, that is not really completed. I need to add some restriction that is called the real zeros of a function. Why do I add that? In this graph, all the numbers are belonging to the set of real numbers. Real numbers are the numbers including integer, natural number, whole numbers, rational numbers, irrational numbers. Okay, why do I emphasize this? In the future, you guys are going to learn another kind of function, numbers is called complex numbers. So be distinguished between the complex number and real numbers. Coming back to see this one, is the zero of a function. What does that mean? Is the function you set that equal to 0, and whatever the x value is, those are the x-intercept. Okay, and this, remember, f of x is y value, so that means y equals 0 right here. So those are the x-intercept. Some function can have more than one x-intercept. Sometimes it does not have x-intercept. It's okay, but keep in your mind that functions can have can have more than one x-intercept. Today we are talking about the vertical line test. Then we know that the function cannot have more than one y-intercept though. So this is very important. Functions can have more than one x-intercept, but only can have at most one y-intercept. So those are the intercept. I want to record that. The next thing I want to talk about the graph is the increasing, decreasing, and constant functions. So what is increasing function? Very quick example. If this is a function in this interval, and let me call this as x1, corresponding will be f of x1, and this is x2. Okay. So this is increasing. We say that for every x1 less than x2 on this interval, let me call this interval is I, and the output f of x1 is always less than f of x2, no matter what x1, x2 are, as long as x1 is less than x2. Then we say that f is increasing on this open interval I. Decreasing, getting smaller and smaller, right? If I have a function, maybe it looks like this. So this is interval I. If I say this is x1 and maybe the x2, still the same condition, f the x1 is less than x2 on this open interval, but this time f of x1, the smaller input, have bigger output greater than f of x2. Then we say that the function is decreasing on the interval. Constant, that means does not change at all. x1, x2, no matter x1, x2 are, the output are always equal to each other. Then we say f is constant on this interval I. Most of the time, the graph is not like simply just increasing or decreasing. It will just depend on the interval. Let's take a look at a quick example for that. Okay, so I'm going to have this function, and let me label some key things. Maybe this -5, this is 10, and that point is A, and this point is 2, and this one is 14. Okay. So this is the function because pass the vertical line test. I'm going to take a look at the increasing, decreasing. So where is decreasing? Even the arrow go up like here, but we are thinking from left to right. So the point, oops, going down, that means decreasing, right? So that is decreasing. So, and where is decreasing? And this side is -infinity, and this side is positive infinity. So from -infinity to all the way to 10, that's decreasing. After 10, oh, mistake, that's -10 because it's on the left-hand side of the axis, right? So from -10 all the way to this point, it's continue getting larger, 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 even though here it gets slower, but still increasing. So that's increasing the interval. So the function is increasing between -10 and 2. We are talking about the input interval. So from 2, this function is okay, does not go up and down, is keeping constant. So in this area or interval, we call that is constant functions. So that is constant. It's between 2 and 14. After x equal to 14, the graph is going to drop down with decreasing, which is that's not a decreasing interval. Is from 14 to infinity. Now for the decreasing, I have two intervals, can be here or there. In the set notation, we will use the union. In this union, or in this interval, or in that interval. So that is increasing, decreasing functions. So hopefully that at the end of this section, you can have some general idea of the basic things of graph of functions. No matter what function we are talking about, those are the things we would take a look. You know, is that a function? If it is a function, what's the domain and range? If you can determine that from the function graph, or what is the z of the function, or is this function increasing, decreasing, or constant, or in which intervals? Alright, so that will be end of the 1.2. I see you in 1.3.